Hi everyone, this is Professor Granucci. In this video, what I'm going to do is talk about conservation of momentum. What I'm going to do is actually break it down to two parts. The first part of this video will just be talking about the concepts, and I'll kind of go through I'll show you the mathematical models and equations at the moment, and then spend video two just going through like a series of problems. So I'll just do them all. So you'll see that I'll skip them now, but I haven't forgotten about them. So here we go, conservation of momentum. So we'll briefly discuss, Newton's third law in regards to momentum. I'll talk about what it means to be conserved. It's actually very similar to energy, so that's the good news. We can relate it to that. And then what we're going to do is break them down into three parts. There's three types of collisions called elastic, inelastic, and explosions. Now, I'll talk about elastic and perfectly elastic and all that fun stuff too. And then, of course, I'll apply some real-life applications to this in addition to mathematical modeling of all of this as well. So this is, again, kind of redundant. It's just another way to think about Newton's laws again. So Newton's law, especially the third one, it talks about interactions. So momentum kind of talks about this case of taking two objects and colliding them together like this. So the most important part to remember from Newton's third law is that when this happens, when they collide, that the force between them is the same. And because of that, we have the consequence of conservation of momentum. It's a really cool, actually, mathematical derivation to go from momentum to all the equations that I'm going to show you. As always, I'm not going to do it in this case, but I can show you if you're interested, but they do all relate back to each other. So basically, this is the study of interactions, what happens when two things collide. And of course, in physics, when you have a force between two objects, that's an interaction. So just know that connection there. So exactly, so we have two objects, they feel the same force. Remember, they'll behave differently based on their mass. And then we're going to basically evaluate the motion before and after collisions. But we're not going to evaluate just the motion, even though I do have it just motion here, it's the momentum, so motion and mass. So that's another important feature of this. So this is just a visual of exactly what I just demonstrated with my fingers here. So we're going to look at things kind of before and after. So you'll notice that when I draw pictures, I always do a before and after. I won't focus on the during. The during is something that we're actually going to kind of ignore when we do conservation momentum. But this is the only part where I will emphasize the during right here. So in other words, again, just being repetitive, is that when two objects collide, they do feel the same force on one another. And it's because of this principle that we have conservation of momentum. Now, another little important part is that this force right here is not what we considered an external force. Because you'll notice in conservation of momentum, same thing with work and energy. If there's an outside force, then things change. This is what we call inside force because this is happening within our system. So if I were to circle this, this would be our system. If something comes from outside, like friction, for example, that's an outside force. So just a quick little distinction. Like I said, you'll never see this image pretty much again, so don't worry about this internal force thing. When we talk about external forces, it'll have to do with friction or pushing something, right? Okay. In short, conservation of momentum says in absence of an external force, the momentum of the system is conserved. So a couple things. Mathematically, I can write it like this. The change in momentum over time should be zero. That's conservation, right? Just like conservation of energy, the change of energy over time should be zero. There's no difference in before or after. I could actually rewrite this. Let me get my tablet. It's not officially plugged in yet. But I could rewrite that same exact equation to what you see right there. And notice that we're considering what is called the total momentum of the system. So in other words, we're not just considering just the momentum of one object, but the momentum of both objects when it comes down to it. And then what we can do is we can rewrite this. Now, so the force on our system is zero. So let me just take a quick second. Sorry about doing this. I thought I had it up. Just one quick little step. There we go. Coming back to this. So let me show you. Actually, I'm going to do a blank page and say delta P over T is equal to 0, right? So notice that delta P is basically the same as me saying P final minus P initial over T. So basically what I'm saying is that the initial, these numbers, the change in momentum has to equal to 0. In other words, that the final momentum minus the initial momentum has to equal to 0. Notice that this can't be 0. The equation will be ill-defined. So the part that has to equal to 0 is this. And therefore, the momentum in the initial has to be the final. So that's kind of another way to write this mathematically. Fun fact 2. Previously in physics, we saw that the impulse is force times time, right? And actually, that's equal to the change of momentum. And notice if I put this on the bottom, that the force is equal to the change in momentum over time. Cool. And in fact, if the force is equal to 0, just like I said before, then we have conservation of momentum. So it's all related, right? Isn't that so cool? I love this stuff. This stuff is great. So in other words, this is just another way to say that the impulse in the system is basically 0, that there is no force, externally that is, that caused a change in our system. So it's pretty cool. And I already derived this for you, but if there is a force, and keep in mind when we talk about force, we're talking about basically, are we considering friction? Are we considering something that is being pushed? Then this is the case. But I'll tell you 100% that we won't actually deal with this. Mathematically, that is. But conceptually, we need to think about it. So like I said, if you're doing, mechanics in your physics major, you would go ahead and consider these cases. But we will not, as discussed. Okay. So let me show you a couple demonstrations regarding conservation of momentum. This is so sad that I can't do it in real life. This is one of my favorite demos. You might be familiar with it, called Newton's Cradle. So here's one example right here. This is certainly not as powerful as what I can do with a real case, but I think most of you know this little thing. There you go. So you've seen this before. But I hope if you really think about this, this is pretty amazing because, first of all, notice that I lifted one, and even though there is 4 more over here, only 1 went, right? These all stood the same. Now, of course, in order for this to really work, there's 2 very important things need to happen. These all have to be hard objects so that they don't deform. So notice that they are, right? They pretend that they're real. They are spheres right here. And the other thing to notice is that they're all the same mass. Like this would have a different outcome. So when I make the transfer of velocity, I'm going to purposely go really high. We see that it goes really high too. Both mass and momentum are conserved. I'm going to go ahead and do a small one to make my point. Very teeny tiny, very teeny tiny. Or another way I like to say this is the in equals the out. So think about this. This is usually what people don't do with this. What if I had 2? If I have 2 in, how many think are going to come out? 2, right? We're conserving momentum. 2m times velocity before has to equal 2m times velocity, like that. So 2 in, 2 out. What about 3? 3 in, 3 out. This blew my mind. I hope it's blowing your mind because it blew my mind. I was like, what? So same kind of idea. We know that we have to conserve momentum. The force, there's no outside force in this system. There's no friction. There's not enough air resistance to slow it down. I'm not pushing it other than releasing it for that first time. So therefore, momentum's conserved. Want to see 4? There's 4. There you go. Exciting. Put it back down. Want to see 5? ridiculously silly, but it's actually, it's still pretty cool because it's still obeying that law. Now, unfortunately, the program doesn't allow me to do it, but I can do this with direction as well. In other words, I can put 2 up here, and I could do 2 this way at the same time, and you would see that effect. But like I said, this program can't do that, unfortunately. So you can't see that happen. But if I did 3 in this way and 2 in that way, it would actually work out too. So I put this link in the slides in the notes section, so you'll notice the links are right here, so you can play with this. I actually recommend that you do, because as always, you do learn when you play, especially when you play with things like this. I don't know, show your sister or brother or parents what you learned today. Talk about conservation momentum. Teaching really helps. It really helps you internalize the concepts. Okay, this is, and it helps you kind of learn something. Especially if you have a younger brother or sister, you can play physics games, fun fact. And you can actually add up to 7 of these things, and you should just it's a little derpy. But you can still kind of see the effect here. This is certainly not as nice as we're kind of used to, but 3 in, 3 out. Impress your family and do 5 in and 5 out. You could stop it, and you could do up to, you could do a silly 2 here. Just like that. Anyway, lots of fun things that you can do with this. Okay. Pretty good demonstration right there. All right, so I will definitely test you on this kind of concept. So I want you to be able to identify if momentum is conserved in a conceptual manner. So if you look at the following cases, cars accelerating toward one another. So make a mental note, think about it. Is it conserved, not conserved? I'm going to read them. A bullet embedded into a block sliding down a rough incline. A skater that is standing in the middle of the ice throws their gloves. Interesting question. And 2 billiard balls collide. So the answers are in the notes, but if you were kind of guessing, number 1 is not conserved. The key word is accelerating. Remember that if you're accelerating, that you're not maintaining your motion, which means there is an outside force. So the word acceleration is outside force. A bullet embedded into the block does conserve momentum. When it actually goes into the block, that's an internal force, not external force, because the system is the bullet and the block. If I said the block is going into the bullet and the bullet's being pushed by, I don't know, a hammer, then there's too many objects. That's an outside force. A block sliding down a rough incline. Rough will infer friction, so this is outside force, so this is not conserved. A skater that is standing in the middle of the ice rink throws their gloves. Hold on 1 second, pause it. Sorry for the quick pause, I'm back. So a skater that is standing in the middle of an ice rink throwing their gloves. There's no external force here, so that one actually is conserving momentum. The skater and the gloves are the system. You need 2 objects in our system. So in this case, it's an inside force, so we're not considering friction. Notice the word ice means no friction. So this is conserving momentum. And 2 billiard balls that collide is also conserving momentum. Once again, when they hit each other, that's an internal force. It doesn't mention anything about friction or pushing them otherwise. So your key words, for no conservation of momentum, you look for the word acceleration, force, pushing, or friction. Those are things to look for. If it doesn't say these, then you can assume it's conserved with that. So you'll definitely see these examples on your next quiz. So I'm going to explain the mathematical model of this. So the sum of the momentum initial has to be the sum of the momentum final to conserve momentum. I wrote it out for you. But I want you to know this. This is incredibly important, that this equation changes depending on the system. Now, what I did for you is actually I isolated 3 types of systems that we will model. If I was going to do different systems, there would be different models, so it would be different equations. But like I said, I'm limiting it to 3. So here's an example. Notice that you have object 1 and object 2, the truck and the car. So the momentum of the truck, for example, I'm adding the momentum of the car. So notice the sum of the momenta here is equal to, so this is like during the collision, and this is the after the collision. The momentum of the truck after plus the momentum of the car after. This is how I'd model it mathematically to see that. But like I said, I'm going to characterize these and give you examples of each type. The first type of collision is called a perfectly elastic, I'm sorry, this is just like a blast of information, so I'm just going to put it all up here anyway. The first type of equation is called a perfectly elastic collision. So perfectly elastic means they perfectly bounce off one another. There is a case of what is called elastic collision where they bounce off, but they do not, they deform and they actually will not keep their energy. But we're not going to do that. We're going to isolate just perfectly elastic collisions where they don't deform at all and we have conservation of energy. So like I said, the biggest example is the fact that they actually separate after they come in contact with one another. So notice that in order to mathematically model this, the momentum, mv, of the first car or first object plus the momentum of the second object should equal the momentum of the first object final plus the momentum of the second object final. So I know it looks really crazy, but this is actually really nice because the equation's already built for you. So your hardest thing right now is to just determine which equations used when. So here are the characteristics. First of all, perfectly elastic collisions are ones that bounce off each other, and mainly that they don't combine their masses. And notice when I do the other case how different this equation looks. Most of the time these objects are hard and do not deform. So great examples include billiard balls and marbles. If you think about it, they're very hard objects, and when they bounce off each other, there's no, they don't deform or anything like that. And usually car collisions. And generally, to be really specific, problems will say perfectly elastic collision to let you know that they're talking about this. And because there's such a small interaction time, that the energy is also conserved. And notice that we talk about it in terms of kinetic energy. And actually, this should be the sum of the kinetic energies. I hope you notice my little error right here. The sum of the kinetic energies before and after should equal the same. Like that. So that's a perfectly elastic collision. Regular elastic collision, energy wouldn't be conserved, but we're not going to do this case in this course. I do it in 110 in more advanced courses, but just to know that that's another case you can do. So here's an animation of a perfectly elastic collision. The point and the main thing to get from this is the fact that the objects do not combine, they separate. It doesn't matter their direction, it doesn't matter that they're going head on, by the way, it doesn't have to be head on. One of them can stop, like you can see here. It has to do with the fact that they're separated. And if you actually add the total momenta before and after, you'll find that they're the same. So if you do 20,000 minus 60 is negative 40, and notice the after is negative 40. The total momenta is the same, not their numbers up top, not their mass, not their velocity, it's the combination of the two. Inelastic collisions have a different mathematical model because in the end, my picture of course is blocking it, they actually combine masses, so notice M1 and M2 right here. So we start off with the first object and its velocity, and then I'll move this out of the way. I don't know if this helps, I have to see it later. But when they combine afterward, they combine their masses and move as one common final velocity. So and here's just, I'll come back to that slide, but here's another approach. So the two objects collide and they stick together like this, and then they move with common velocity. Another great example, which I'll solve later, is this person running on a sled. Has anyone done this before? Because I have. So a fun thing right there to do. I don't know if my video came back. I don't know what happened here. Oh, that's pretty cool. I'm just playing with my stuff. Ooh. And maybe I don't want to play with my stuff right now. Okay. Oh, this is for PowerPoint. Oh, that's kind of cool. All right. Anyway, point being is that the objects combine. So some examples include combining masses, locking bumpers. So problems might say the car bumpers might lock, jumping onto an object like a skateboard or a boat or a wheelie chair or something like that. And generally, these cases do lose energy. So their initial and final energies will not be the same because of the fact that the objects deform when they do that. Okay, so you saw some of these examples. These are inelastic collisions. Notice the difference now. Notice that they're together. So that's the biggest point I want you to get out of this, is they stick together. That's inelastic. The last type is called an explosion. Explosions start at rest and then move apart, as you might imagine. If you think of like a firecracker, I hope my video is still going, and then it goes out like that. So that is what an explosion does. But it doesn't have to be an actual explosion, by the way. So it could be two people pushing apart, like in this case right here. If you're on ice skates and you and a partner push each other out, this is an explosion. Another explosion example, here's like in space, another way of thinking about it. Another explosion example is this, taking a wrench and throwing it away from you, or like the gloves one I mentioned earlier, because you both start with the object and then you both move apart from the object. That's an explosion example. Another common is a bullet and a rifle, kind of like a recoil. If you take a bullet and a rifle and you recoil out. Fireworks are perfect examples of this. And then when two people push apart. So what happens is that you start off with no momentum because the objects are not moving. And then you go ahead and figure out the total momentum afterward. And if you notice the mathematics of this, if I take this whole side and move it over, one of them has to be moving opposite the other. That's a really important part about explosions. And naturally, the energies don't match because the initial energy is 0 and the final energy is different. So it's not going to have the same energy in this case either. So like I said, this is an example of an explosion right here. And then what I'm going to do in the next recorded video is actually go through these as you might see them on your homework or on your, you'll definitely have one of these in your upcoming quiz, very much like it. And I'll ask the very same questions, you know, what type of collision, which quantities are conserved, i.e. is it momentum or energy, what was the speed of puck A before collision, calculate the change in energy during that collision. So I'll go through and do all of that for you. And then same thing here. And here, and here, and here. So lots of example problems. I'm just going to mention this. We're not going to cover this in the course, but momentum is actually conserved in all directions. So if I was doing in 2D, we'd have to find the momentum in the X direction and the momentum in the Y direction. Once again, I'm not going to do this as part of our course, but this would be, it's not hard, it's just long. This would be easily a 20-minute problem I would have to solve. But, you know, if this is offset to this, these would move at an angle. And momentum is still conserved in this case. So in other words, they're both, this one's moving totally east, then the momentum of this has to be totally east, which means the ups and the downs have to cancel. That's the concept of this. And if you want to try this out, I have the solutions in the slides like this. So in the next video, I'll go through the mathematical models of these equations.